Hello and welcome to this tutorial on finding the torque in a DC machine. This question is often given by examiners because it requires the student to know a little bit more than simply derivation around Ohm's law to find stuff in DC machines. It actually needs them to sort of understand a little bit about what's going on. So it's a good second tier question to ask. So we'll look at a machine. We'll pretend we've got a machine and we've got some measurements. Let's say it's a series machine. So series machine, we have it's normally drawn out to have our field resistance here, our armature resistance here, our idealized rotor here with a back EMF, and there are various things that we can measure here. We can measure the input voltage, we can measure the current, we can measure the value of those resistances, and EA we can't measure, but we've got expressions for it. So let's just say we're trying to find torque. We can measure the input voltage. Let's say we've measured that input voltage and it's 400 volts. And we can put an ammeter in series and we can measure the current coming into the armature, which is what we're interested in. In this case, the current's also going through the field because it's in series. Let's say that current is 55 amps. We can measure the value of the field resistance and the armature resistance if we turn the machine off and disconnect it and do those appropriate measurements. And let's say we've found those and the armature resistance is 0.2 ohms and the field resistance is 0.6 ohms. We can also measure the rotational speed of the machine. That's easy enough to do as well. And let's say we've got a rotational speed of the rotor that's at 450 radians per second. Now, the other thing we need to bear in the back of our mind is a couple of equations that we've got for DC machines, which are very useful equations. The first one of those actually applies to what we're looking for, and that is to find torque. We need to know what the machine constant is, what the flux in the machine is, and what the armature current is, and that will give us torque. The other one we know is the measure of the back EMF, and with the back EMF is also a product of the machine constant, of the flux, and the rotational speed. Now, going back to our equivalent circuit, we can see fairly obviously that this is a series circuit, and first year stuff you learned around the sum of all the voltages and all that sort of thing carrying on. We know that the voltage here that's being applied to this machine will be the sum of all the volt drops across here. So that will be, and this is a series circuit, so it'll be the current times the field resistance for the volt drop here, across here, and the volt drop across here, which will be the current times the armature resistance, plus the back EMF that's being generated here. Now, that gives us enough to solve this. We've got an expression for torque that requires us to know K phi and the armature current. Well, we know the armature current. The current through the armature is 55 amps. We don't know what K phi is. We don't know what K is. We don't know what phi is. We don't need to know. The reason is because we can find out a value for K phi taken collectively from this expression here, where K phi can be found by knowing the back EMF and the rotor speed. We've measured the rotor speed, we know what that is, but we don't know what the back EMF is. But we can find it out, and we can find it out by looking at this equation here. We've got an expression that involves the back EMF. In it, we need to know the armature resistance, the current, both of those we've measured, we know. We need to know the field resistance, again, we know that, and the voltage. So we can rearrange this equation to solve for the back EMF. We can then rearrange this equation to find K phi, knowing the back EMF and the rotor speed. And once we've found K phi, we can insert it into this equation. Knowing the armature current, we can find torque. And that's what we're going to do. So we rearrange this here. So that'll be the input voltage minus the current times the field resistance minus the current times the armature resistance. Put some numbers to that. That's 400 on the input minus our current is 55 times our field resistance is 0.6 minus our 55 times 0.2, which will be 400 minus 33 minus 11, which gives us 356 volts. So that's what our back EMF is. Now, one of the nonsense tests that I always get my students to do is to consider that the back EMF is almost always going to be 80 to 90% of the input voltage. So 356 to 400 is within the ballpark. This machine is operating as a motor, so the back EMF will be less than that voltage here, and it is. So we've passed that initial nonsense test. Now we know our back EMF, we can insert it into this equation here with our rotor speed to find K phi. So we can rearrange that. K phi will be our back EMF over our rotor speed, which is 356 over 450, which gives us, and I'm not doing that off the top of my head, 0.791. We can then take this value, insert it into here. Torque is K phi times the armature current, which is 0.791 times 55, and that comes up to 43.51 Newton meters. And that's a believable number. We can believe that. So that's how we do that for a series machine. To do it for a shunt machine, we've still got all these measurements. If this machine with these things was the armature resistance is not going to change if we configure it to shunt. The field resistance is not going to change if we configure it to shunt. These equations don't change. So we'll go through it and do it for a shunt machine as well. We're going to make a few assumptions in that process. So let's look at a shunt machine. We've got our field here, our armature, our idealized rotor. So here it is for a shunt machine, or if we looked at it for a separately excited machine, we'd have our field over here. Okay. And what we're going to do is we are going to assume that the current that we've got flowing here through our armature is our same one. So we'll be extra clear, clarify that. That is the armature current is going to be 55 amps. What the field current is not going to worry. It's not really relevant to what we're looking at here, so we're just going to forget about it. So we'll assume everything else is the same. We've still got the same armature resistance. We've still got the same, everything else the same speed. Everything we've talked about still applies. The main difference is this equation here is going to be different because our voltage here is going to be the sum of the current, the volt drop across the armature resistance here, and the back EMF. So we rearrange that. We don't have the field term in it. We rearrange that, and we end up with a says that IRA. We put some numbers to it. It's 400 minus 55 times 0.2, which gives us, that comes to 11. So 400 minus 11, that'll give us 389 volts. Again, within the ballpark, the numbers we've talked about. Again, it's less than the input voltage, which is what we'd expect to see for a motoring configuration. We can follow the same process. We can find K phi, which is the back EMF over the rotor speed, which will be 389 over 450, which comes out to be 0.864. We can then use the same equation K5 times the armature current, 0.864 times 55, and that gives us 47.5 Newton meters. So that is how we find the torque in a DC machine, irrespective of whether the machine is configured in series or shunt. It's quite a straightforward process. It just needs you to understand the sum of all your volt drops, which you should, as when you learn that sort of stuff in first year, and then be able to manipulate these two equations. Thank you for watching. I'll see you again soon.